All right, so final lecture for Tools of Operations Research. So we've covered data mining, we've covered forecasting of time series, we've covered optimization, specifically linear optimization. We've talked a little bit about other kinds, but we've only really practiced or exercised linear optimization, but several different forms of it. So the last thing we're going to talk about is simulation. Okay, all four of those techniques broad techniques we've learned this semester are all tools to use in operations research. Remembering back to first lecture, operations research is about making informed decisions. That is, using data and models to help either better our understanding or predict what will happen, or predict an outcome with different parameters or different inputs. And using tools like that with these kind of models we're building, or the data we use to build them with, to make that better understanding and those predictions inform us so that we can make better decisions about what to do or not to do. So thinking back, we talked about assignment 5, and in one case we were deciding how many product of different kinds to make or subcontract and buy. Now, that's a very complicated question in the real world, but we might have built a simplified model about how much we think things cost and how much time we have to build and do different stuff. And we can use that to sort of discover or understand the pattern that says, well, it's better to make things if you can, and here's the constraints of which, say, department or which budget or something else is limiting you from doing more. But it also helps us answer the question of, is it even worth subcontracting, and how much should we think about subcontracting out for somebody else to make the units for us, and so forth. So all of that was a model, or an example of a model that used linear optimization, but really it was helping us make effectively some kind of decision about what's the best decisions to do, how many things to make, which product of the two different types should we focus on making, which should we focus our efforts on making one product but subcontracting the other one, or some blend of all of it to make the best profit. Okay, so we were using that to make a decision about what to do. Now, we did that either through a better understanding, identifying a pattern of what optimal solutions would look like, or predicting how much we would make based on the model. Same thing for data mining, same thing for forecasting, and now the same thing for simulation. These are all just techniques. They're tools. They're algorithms or methods we can employ to help us understand, help us predict, and help us make better decisions. Okay. Now, specifically, talking about simulation, talking about optimization, what the objective is to find optimal decision variable values. So we have some decisions we need to make. We get to decide what value, whether to do something or not, or how much to do, how less not to do, whatever the problem calls for. We're trying to define which values can we decide on that give us the best or optimal objective. Okay, and the objective was just a function, maybe a somewhat complex one, but a function of those decisions, the values we decided on. In the linear optimization case, it's a linear function. In nonlinear optimization, which we didn't really do, the function can be nonlinear, okay, and so forth. However, there's something that these optimization techniques don't really handle, or don't really discuss or address, and that is uncertainty. What if you don't know what value, how much something will cost? What if you don't know how much of something you could actually sell? That is, if we were deciding how many, or in one case we decided how many chairs, desks, and tables to make, and we were told in that case the maximum number that we could sell. That is the maximum number you should ever make, because no one will buy beyond that limit. But in the real world, you wouldn't necessarily know that. That would be an aspect of uncertainty. That is, you might have an idea, you might have maybe some bounds, a maximum, a minimum you think that thing might be, but you're not sure what value it really is. Okay, optimization, that tool or that technique, doesn't really take that into account. Optimization assumes you have defined functions for your objective and your constraints. Right? There's no randomness. There's no variables other than the decisions you make. Okay? There's no other variables into the model. Simulation is going to address that by handling this thing called uncertainty. Okay? So uncertainty specifically may be in values of the model parameters. So let's say we were uncertain of the exact cost of producing a single unit of something. So we're going to decide how many to build, but we don't know really how much it will cost to build it, partially because it depends on buying material, sometime in the future when we're going to build it, and the cost of material fluctuates. It may go up, it may go down. Again, we may have some level of certainty. We know it's not going to be less than $10 and not more than $50, but we don't know what value it will be within that range or something. So that's where simulation comes in. Simulation is the technique specifically of selecting, I'm going to say random values. I'll put that in quotes and I'll explain that in a minute. We're going to select random values for these uncertain parameters, the things we don't have certainty of. We're going to pick random values for them, compute a model that is some objective or result or whatever it is, and then we're going to repeat that process with newly selected random values. And we're just going to do that over and over and over, okay, until we've effectively picked lots of random values that we think is very representative of all possible values that that parameter could be. Okay? What that will give us then is effectively a range of values for the objective or the result. So if we said, for example, we're unsure of the cost for producing something, but we think it's within a certain range, we can randomly pick values in that range, compute using the model how much money we would make profit-wise for all those different possible costs, and effectively in the end what we would have is a range of possible values for profit based on randomly selected values from the range of values for cost, okay, through our model. So while we may not come to one specific answer that would say here's how much money you can make profit-wise, what we could come to is here's a range of values of how much profit you can make. You could even come to more specific answers like here's the probability that you make at least this much profit or more, or the probability you make a certain amount or less profit, or the sort of expected or most probable profit value you could make. Okay, so there's lots of outcomes that you can get out of simulation. Lots of sort of lots of objectives, right? Things you can answer, how much or how likely certain things are, what the range of the objective is, but you'll never get one answer. The actual value is X, right? Because you're uncertain about the parameters to the model. Okay. All right, so let's do some examples. We'll best see this through examples. We'll do two specific examples which will hopefully illustrate pretty much everything there is to see about simulation, and then we'll close out for the night. Okay. So example number 1. Butts and Stores faces a problem in maintaining sufficient cash balances for operations over the first 6 months of the year. Okay. So we have this store. They have cash that they use to cover costs and other things. And throughout the first 6 months of the year, they want to make sure they keep enough cash on hand, enough cash to invest or buy or whatever they need to do. So each month they have to pay fixed costs and taxes. So they have to pay for electricity and rent and payroll taxes and things like that. Those are fixed. That is, they know how much they're going to have to pay for that. Okay, so that's not an uncertain thing. That's a known amount. But they also have to pay material costs for how much they're going to build and sell that month. And the material costs are about 80%. So if I can sell something for $100, generally speaking, in this problem, we're going to assume I have to spend $80 to get the material and build and make it, so I can sell it for $100. Okay. Now, the key is every month you sell some product, you have to pay the material costs, but you don't get the revenue from those sales till next month. So people sort of buy on credit, effectively, and you sell it to them today, but you don't get paid till next month. So here's sort of the discrepancy in that you need to make sure you have enough cash to pay your material costs for the things you build this month, but you're not going to get paid for them till next month. Next month, you'll use that cash that you get coming in to pay for the materials that month for building the things you'll sell that month, and so forth. Okay. Now, there's a few other things that can happen. One is if you have extra cash on hand, you could put that in the bank and get interest on it, 0.5%. Okay. However, if you don't have enough cash, you're going to have to take a loan from the bank. Okay. And specifically, the company has a policy that says you have to have a minimum of $250,000 in cash. Anything less than that, certainly if you have less than zero, you need to take a loan so that you have $250,000 of cash on hand. However, loans have to be paid back. Okay, and I believe the interest for that is 1% paid back next month. Okay, so if you have extra cash left over, you get some interest from the bank. If you don't have enough cash, you take a loan and pay higher interest than you would get otherwise back to the bank. So we know how much we sold in December. We're going to use that to know how much cash we have starting in January. And now we're going to build a model for 6 months, January through June, to figure out how much cash coming in, going out, and everything will we have, and will we ever have not enough cash that we have to take a loan out? How much of a loan would we have to take out, and so forth. Okay. Now, so if we finish a month with less than the minimum $250,000, you take a loan for 1%. I said that. Principal and interest are repaid, so you have to pay back the loan plus the interest next month. Now, our marketing department's made estimates and sort of mean and standard deviations of how much sales will do January through June. But those things are uncertain. We can't know the future. We don't know how much we'll sell. We just have some idea, okay? Sort of a expected value and a deviation from that we think higher and lower it might go. So given that uncertainty, we want to know how large of a maximum loan are we likely to have to take out in any of those first 6 months. How likely are we to exceed the maximum loan we can take, which is $750,000? That's our credit limit. And then we'd like to know how much loan interest cost we're going to have to pay back. So if we had to take 2 loans, we're having to pay back interest twice, right? What's the total number or total amount of interest we have to pay back? Just as something we want to know. So do we need to take a loan? How big of a loan? Is it too big? And how much cost do we have paying interest back for the loans we take? So those are all things we want to know or answer given this situation. However, there's things that are uncertain. How much we'll sell isn't known. It's an uncertain parameter. So we're going to have to simulate, randomly select values given sort of the guidelines we were given, okay, which are here. So given some guidelines, we're going to simulate how much we might sell, figure out if we will take a loan, won't take a loan, how much, so on and so forth. And then we're going to repeat that process, resimulate new sales numbers, recompute the model, how much loans do we have to take, and do that over and over. Now, generally speaking, there's not a right number of times to do the simulation. It depends on the problem, it depends on how complex the model is, and so forth. In this example, and for the examples we'll do in this class, we'll generally simulate 1,000 scenarios, 1,000 possibilities. So 1,000 times we'll simulate how much we sell in 6 months, how many loans and how much of loans we take out, 1,000 times, and use that to answer questions like, what's the probability that we have to take a loan out that's more than our credit limit? What's the most probable amount of a maximum loan we would take? Or what's the most probable amount of the interest we'll have to pay back, and so forth. Okay, so let's move to Excel. Luckily, I have an Excel sheet already for this. And I believe it's this one here. Nope, it is not. Okay. That was a good guess then. this one. That's what I was looking for. Let's see here. Here we go. So let's look at it's going to be this one here. Yeah. All right. So here's an Excel spreadsheet that represents those things. Okay. Let's get rid of some of these comments and stuff. Okay, so here's the model. So we have our monthly sales. We know how much we're going to sell in December. That's already happened. That's certain. However, for January through June, we don't know how much we're going to sell. What we know is a mean or expected number we'll sell and a standard deviation. Now, we'll come to this later, but what that implies is we're going to use a normal random value distribution. We'll explain that in a minute. Effectively, you can think of that as saying we think we'll sell 1.8 million is what this represents, plus or minus 80 million, okay? Or plus or minus some value based on 80 million. So, okay? So we may be higher or lower than that expected value for each month. And the amount higher or lower we might be, or the amount of uncertainty there is governed by this thing called standard deviation, okay? Now, we also know our fixed cost, the taxes and fixed costs we have to pay. It turns out we have to pay more of those in March. So there's kind of the right before tax day, right? In April, there's more taxes to be collected, more costs to be paid. But generally speaking, those things are known. They're not uncertain, how much cost we pay each month. And the other known things are how much the materials cost. It's 80% of sales. So if we think we'll sell 1.8 million, we need 80% of that paid in January to build or make or buy or fabricate or whatever we do the product that we will sell for 1.8 million. We have to pay 80% of that in costs. The interest cost of taking a loan out, we have to pay it back with 1% interest. The interest returned on extra cash we have, 0.5%. And then the last two things, not really necessarily parameters, but things to keep in mind. That is, we start January with $250,000, and we want to make sure every month we keep at least $250,000 on hand. That is, if we ever end a month with less than that, we'll take a loan out to make up the difference. Okay, so here's what we have. So the actual sales. So this up here defines sort of the parameters for our model. Down here is going to be sort of our real model, the calculations involved. So we sell 1.54 million in December, okay, which means in January, the receipts, the cash we have comes in from last month's sell is $1.54 million, okay? If we think we're going to sell 1.8 million, so right now we just have this value set equal to the mean, equal to the expected value. So if we sell 1.8 million, well, that means a few things. One is we know our fixed cost, they're $250. Our materials cost is 80% of 1.8 million, or 1.44 million. Okay, so those are costs we have to pay in January. We start January with $250,000, which means that money in the bank gets us 1.3 million in interest. That's 0.5%. And then, of course, we knew how much money we had coming in from December. So this is revenue coming in, costs going out. Okay, so we can effectively compute all the revenues added up minus all the costs. This is what that is here. And we realize at the end of January, we would end with $101,000. That's less than the minimum we want to end with, which is $250,000. So this next line here computes what is the loan amount we need to take. And the clever way they computed this is, what's the difference between how much cash we ended the month with minus, well, what's the minimum amount minus the cash we ended with? Okay, so that difference, the maximum between that and zero, effectively assures we never take a negative loan, right? At best, right, we need a $0 loan, okay? Otherwise, we might need a loan for some amount, which is the difference between $250 and this amount, okay? So in January, that means we need to take a loan of $149,000 added to the $101,000 we ended with, so that we finish the month with $250,000. Okay, so now we end January with $250,000. That becomes the amount of cash we start February with. So now we need to know, well, that money in the bank, we'd get interest on it. So we took a loan, but we put the money in the bank and got interest on it. Okay, we have our sales that came in from our January sales numbers. So all of that is money we have. We have our fixed costs, material cost, which is the 80% of our February sales number. We have to pay back the loan we took in January, this $149,000. We have to pay that back, plus we have to pay it back with interest, 1% interest. So all of those things represent costs. So our revenue minus our costs means we end February, or revenues minus costs means in February we'd have $451,000 cash left over, which obviously means we don't need to bother taking a loan. We have plenty of cash, more than $250,000, so we end February with just $451,000. That becomes our cash for March, and so forth. So you can see how this sort of trickles month by month. Each month you get money coming in, you pay costs, if money goes out. Whatever that difference is, if it's not enough, not $250,000, you're going to take a loan. So you figure out how much money you end the month with. Then you start next month with that much, figure out what happens next month. You pay back loans if you have to, and so on and so forth. The key is, there are two things we wanted to compute. One is, what's the maximum loan amount we had to take? That is, of all these loans we took, in that line there, line 29, what was the biggest one? Okay, and in this case, we had to take a $648,000 loan. Okay, we took it in April, which makes some sense because March is when we had to pay sort of higher costs and so forth, and so we may have ended March with a little less cash, which means in April, you know, if you didn't get enough sales amount coming in, you're really going to be hurting for money, okay, and so forth, which is why generally it looks like April is our worst month as far as needing to take a loan. However, the loan we took is less than our credit limit. So if we sell this amount each month, specifically, we will never have to take a loan more than our credit limit. And we know the sum of all the interest paid, so all this row here in 27, the sum of all our interest paid is about $12,000. Okay. So, sounds like a lot to me, not necessarily to a big business. Okay. All right, so that takes care of the model, except for the uncertainty part. Okay. So we assumed here each month that the amount we sell is exactly equal to the mean or the expected amount we'd sell. What we haven't taken into account is that number may be more or less, okay? And we don't know necessarily. We know about how much more or less, but we certainly don't know within that range where what will happen, okay? So I'm going to flip to the next sheet here. Same thing, same model, same everything, except now our sales numbers, okay, for each month, January to June, is computed. It's not an exact value. It's computed using this special function called PSI normal, which means I want you to randomly select a value from what's called a normal distribution with an expected value of, in this case, E6, 1.8 million, and a standard deviation, that is a variance, how widely that random value can fluctuate up and down, of about 80. Okay, $80,000. And so what you'll see here is the value it's chosen, in this case, is $1.859 million, and so forth for February, March, April, each using that month's mean and standard deviation. We've now randomly computed some values, which means we now have a different answer about the maximum loan we take and the loan interest we'd pay back. Okay. All right, I want to make sure that makes sense. So all we've done, we've taken the model. In this case, I used a pre-built model, but here it is, computed the things needed to be computed, and now we've integrated into that these special functions, PSI normal in this case, to randomly select values for us to simulate with. So now because we don't know, we have uncertainty, we're just going to randomly pick some values based on some given range or some given idea of what value it could be or close to, but randomly pick some. Okay. Now what you can do, I'm going to show you, if you double click on these cells, it will show you what's called a probability distribution graph. There it comes, which basically says what's the probability of any given value. So that distribution with a mean of 1.8 million and a standard deviation of 80 million gives you values roughly from about 1.5 million to 2.1 million. But the most likely values are here in the middle, close to 1.8. That is, those values have a high probability that we think that's the sales number. But there's a really small chance we might have a really high sale or a really low sale for that month, right? And in fact, if you look over here, you'll see the mean and standard deviation are those two cells we referenced. And scrolling down, it's not there. See, up here you can see, so there's a 90% chance, 90% probability that the sales value for that cell I clicked on will fall between about 1.66 million and 1.93 million. Okay? There's a 5% chance it's less than 1.6 million, and a 5% chance it's bigger than 1.93 million. Okay? So that's what these values up here are telling you. They're giving you an idea of how variable, how random that function or that value for the sales in January could really be. And you can actually click and drag these things around to get a different idea. You can even click on the values. I've already clicked on one. There you go. And type something in. So I can say, well, with 10% chance, right, how low might my sales numbers be? Well, there's a 10% chance that my sales in January will be less than 1.697 million. Okay, so that's what I've asked here. I put in 10% here. It told me what value this line has to go up to for the sales number to make it 10% likely that the value randomly selected will be down below that. You could ask different questions like, well, what is the chance that I will make less than $1.7 million in January? So I change this value up here and then read the percent. So there's a 10.56% chance I make less than $1.7 million in January. And you can do the same for all the rest of these numbers or these parts of this distribution. And again, this is showing you probability of the value being selected. And you can do that. All of these 6 months use the same probability, the normal distribution. So they'll all look the same, except that their mean and standard deviation are different each one. So if we looked at, say, the April numbers, if I looked at that distribution, you'll see that the mean, the expected value, is 2.6 million, and the standard deviation being higher means it's a wider graph. That is, that there's a wider range of values it might be. So it might go from as low as something like, 2.15 million up to about 3.05 million or something, and so forth. And you can again play with the percentages or the values to figure out exactly what probability of getting a certain value or less, or certain value and greater, and so forth. Now, the real key is, now that we've built a model that incorporates this uncertainty, we can compute the certainty or uncertainty of the objectives. That is, I know, or I can simulate maybe 1,000 different numbers for these sales numbers and measure all the values for the maximum loan amount. And I can build a probability graph, like we just saw, for the objective based on the selected values for the inputs. So if I double-click on one of these cells down here, okay, and there's a special value in those cells that I'll talk about in a minute, but if I can double-click on either of these, and because we haven't actually run a simulation yet, we need to say yes to run it. It'll take a few seconds. So here we go. In literally less than a second, it ran 1,000 randomly selected values for our January to June sales numbers. And this is the probability distribution of the maximum loan we would have to take. That is, on average, the mean, on average, we had to take a loan of $648,000. However, sometimes, depending on the sales numbers randomly selected, we might have taken a maximum loan for less. Sometimes we had to take it for more. Okay? But this graph, like the ones we've just seen, is now representing the probability of certain values of a maximum loan taken. So you can again play with some of these values and ask questions like, well, if I'm really concerned about the probability that I have to exceed $750,000, what's the probability that I need a maximum loan greater than that in all of those 1,000 scenarios, all of those 1,000 simulations? And in this case, there was a 16% chance. So in 16% of those 1,000 scenarios, right, we randomly picked some sales numbers that resulted in it needing a loan for 1 or more months that exceeded $750,000. That is, there's a 16% chance we will we will need a loan bigger than we can take, more than our credit. Meaning there's an 84% chance we don't. Okay, better chance we don't, but a non-trivial amount, or non-trivial chance at least, that we might need more than we have credit for. And you can again play with some of these numbers. You can ask different questions. You can say, what's the lowest, 25% of this graph? So there's a 25% chance that the maximum loan we will need is $581 or less, meaning there's a 75% chance the maximum loan we need is $581 or more, okay, and so forth. And again, you can click and drag, you can type in numbers, you can, same things that are computed over here. In fact, a few things I'll show over here, the statistics on the right here will actually give you the actual minimum value, actual maximum value. So in those 1,000 simulations, in the very best case, the biggest loan we had to take in those 1,000 cases, the biggest loan across all the months we took was $314,000. Not terribly large of a loan, biggest loan, but that was the best scenario, right, of the 1,000. The worst scenario in those 1,000 was there was one scenario in which probably we had low sales numbers, and we ended up taking a $1 million loan, or needing a $1 million loan, right? Far beyond our credit, and obviously very large. Okay, so that kind of gives you an idea of the variance, the variability, okay, of how big of a loan we need to take. Again, based on the variability of the model, that is the variability of sales numbers. Those can fluctuate. Those were uncertain, meaning how big of a loan we have to take is also uncertain. But we can measure through simulation how big, how small, how probable, how likely different values for that objective are. Okay, there's many more statistics over here. Okay, I'm not even going to try to talk about any of them. You're welcome, if you know statistics, You might recognize them. You might be able to do some meaningful analysis with them. If you don't, you will not need that information for this class. Okay, at most, what I would ask you in this class is about this first statistic mean, which is the average objective function value. That is, there was a 50% chance we needed a maximum loan of 648 or less, a 50% chance we needed that or more. So it's just the value in the middle, okay? The one that has an equal chance of being less or bigger in all the scenarios. The standard deviation gives you, again, sort of a guide for how variable that objective is. So we think on average we'll need a loan for 648, but we might need one for 100 or more thousand bigger or 100 or more thousand less, okay, that you can see. And I might ask you about minimum and maximum. So the best case and worst case, okay, depending on whether you want a low number or high number. In this case, you're taking loans. Best case, you'd want a small loan, right? So a minimum number. Worst case, you have to take a big loan, the maximum number. Anything else over here, I wouldn't ask you about in this class, okay? Again, there's statistics, there's theories and other things behind what these values mean and how to use them. I'm not going to ask you about it in this class. We're just not going to have time, okay? So that takes care of sort of what is now you can save changes, save the values you input over here and such. It's not really changing anything other than if you open this screen again, you'd see the same thing. But that takes care of what's the maximum loan we'd have to take. You might also ask, how much loan interest are we going to end up paying? Okay, so on average, if I click on this, or double click on this, on average, mean, which is shown here on the screen or over here on the right, on average, we have to pay back about $12,000 in loan interest, $12.37 thousand. Okay. Just reading what the values here are, there's a 5% chance we will pay back $14.5 thousand or more in loan interest. There's a 5% chance we'll pay back $10.18 thousand or less of loan interest. Okay, and a 90% chance we'll fall somewhere between those two. Again, we might ask questions of how much loan interest might we have to pay back with 25% chance. Well, we might pay back $13.28 thousand or more with a 25% chance. On the flip side, there's also a 25% chance we'll pay $11.51 thousand or less. Okay, and a 50% chance will be between those two, so forth. Looking at these statistics again, the minimum loan interest we paid back, again in the 1,000 scenarios, the 1,000 randomly selected sales numbers that we used, okay, the minimum loan interest we paid back was $8.36 thousand. The maximum, $16.44 thousand. Okay, so again, whereas the maximum loan amount we needed, right, was something in the $648,000 range with a pretty big variance, the amount of loan interest we pay back is comparatively a smaller number with less variance. That is, it's in a tighter range of values that are much smaller, okay, just by virtue of what that thing is measuring. But all of these are questions we could ask or be interested in. So again, if we were interested in what's the maximum loan amount we'd need to take, we could simulate sales numbers, okay, and compute the probability or the distribution of maximum loans we might have to take. And from that we can say what's the most likely maximum loan we'd have to take, the mean or the average. We could say what's the worst case or best case, max and min. Or we could say, if we're interested in a specific value like $750,000, we could say what's the probability that we need a loan that's at or bigger than our credit, the loans we can take, which is $750,000, and that answer was 16% chance we need more than we're allowed to borrow from our bank. Okay, any questions? I'm sure there might be some. Any questions about simulation? thrown a lot of screens up there. I know that, and that's all right.
So basically, everything above what's set up, and then we had to go back down to the objective function to make it actually run and simulate the quantity that we.
Yeah. So this model, this Excel sheet that we built. Like pretty much any other we've done so far. Now, some of these, I think all of this is pretty much linear functions. They wouldn't have to be. But yeah, we're just computing values. The only difference between what we've done here and all the examples of optimization and forecasting and other things we've done is we've now introduced these special functions that represent randomness or uncertainty. Yeah. And those are based, now the uncertainty is bounded. That is, there's parameters to how uncertain it is. And we have ideas about how uncertain. So we knew the sales numbers for January, that they're not anything. They're something close to 1.8 million plus or minus some variance or variability. But we don't know the exact number. So that's where simulation will come into play by randomly picking values in those ranges or in those probabilities. And then whatever we could be interested in computing average final cash value in this column. So if we averaged all these numbers, we might be interested in graphing or seeing the probability distribution of that. There's not necessarily just one objective that we're interested in when we do simulation. We might be interested in looking at multiple facets of the model. So in this case, we were curious maximum loan. We could have been curious in average loan or the sum of all loans. And we were interested in loan interest, that it's the sum of how much interest we have paid. We might have been interested in maximum loan interest paid in any one month or something else. Yeah. But all we've done is we've taken a model, just computations, calculations, equations, computing things with some uncertainty built in, some uncertainty quantified and built into the model. And then we've used simulation to sort of extend that uncertainty to how uncertain is the objective, how uncertain or variable is the output or the outcome that we're interested in measuring. Now, the one and only thing I didn't answer yet is when you have the cell where you've computed your objective or objectives that you're interested in measuring, you have to add to that cell. This is a little strange. You have to add to that cell, meaning plus at the end, this PSI output function. I don't know how that works. Okay, I'm not going to pretend to know how that works. All that does is that tells the software, Analytic Solver platform software, that the value in this cell you want to sort of capture and build that graph with. Okay, so when it's doing simulation, picking random values, 1,000 times over, it's keeping track of which value this cell, what value was computed in this cell each time, so that it can make those pretty graphs and track minimum and maximum and other things for you. You have to tell it through this PSI output which cells you're interested in doing that for. Okay, so in this case we had two cells with that function, that output function, so two things we were interested in. There's not, that I know of, any specific limit. Some problems you might have one output you're curious about, and that's all. Sometimes you might have 10. It depends on the problem. Question?
I may have missed it, but where would we input the number of trials that we wanted to run?
Oh, yeah, so great question. So the question was, where would you input the number of trials, the number of simulations? So what I didn't show you, I just double-clicked on the output cell, and it sort of told me you need to run simulation, and I had the option to say yes or no. What you could do is go to the Analytic Solver platform tab, and there is a Simulate button here, where you can either say to, for this class anyway, you would just say to run once. Okay. The other option is if you had a farm of servers to do complex simulations, like millions of simulations for a complex thing, you could use some server setup to do that work. Obviously, we don't have that here in this class for this assignment or anything. So really, you would just say run once. That does the same thing as double-clicking and saying yes. And in this case, what it brings up in the end is the distribution. I think these are of all the inputs and outputs. So you'll see here cell, say E18, which is the sales numbers for January. This is what they look like in the simulation. and then cell, C32, which is the objective of maximum loan. That's what this one looks like here. And I think you can even double-click them in this way to bring up that same screen we saw before and so forth. So different ways you can get to it. It's all giving you the same information. Haven't yet answered your question, cancel, which is how do you pick how many trials or scenarios to do? I believe that's in this options button here. Look real quick. Then this is where I'm going to have to say, here it is. Look at how many more options there are. For this class, you don't have to care about them. If you were a serious, practitioner of operations research and you did this for a living and you used a tool like this, you likely would need to understand what all these different things mean or when to use different values or so forth. In this case, for this class, in fact, you will always be okay using the default, which is 1,000 simulations, and the default for everything else, which effectively controls how much variability and how it picks its random values and other things. But for us, we'll just, the standard defaults are fine. But yeah, you could here say, instead of 1,000, maybe 100 or 10,000 or whatever. Okay. All right, that takes care of an introduction to simulation. So again, just to recap, we use simulation when we have uncertainty, when we don't know specific values to use in the model. Now, you do have to have an idea of how much uncertainty, because you have to parameterize, the variability. What's the maximum, what's the minimum, or what's the expected and the standard deviation and so forth. But you do have to have some idea, but you're not sure exactly what value may be in that range or exactly what value overall to choose. You can have multiple parameters that are uncertain. So in this case, we had 6 month sales numbers that were all uncertain. They were all uncertain in different ways, but 6 uncertain variables. And you can have multiple objectives that you want to measure uncertainty or the effect of the uncertainty on these objectives. In this case, we had 2 objectives that we wanted to measure. Okay, so again, I just want to contrast real quick. In optimization, you have decisions you're making, you have constraints, and one objective that you're trying to optimize. Okay, in simulation, you don't really have decisions. You're not trying to decide anything. You're just wanting to say, I have some uncertainty with how things work in the real world that I want to represent, and I want to measure what happens to some outputs, one or more, given that uncertainty. So we weren't deciding, we're not optimizing anything here. All we're doing is saying, here's the scenario, here's kind of how the world works, or the business works, but we don't know the future, so we can't know how much we'll sell each month, but we'll project or assume we know some bounds on that uncertainty, and we want to measure how the variability of that uncertainty, those variables or those parameters, affect the variability of an objective we want to measure. Okay, so multiple uncertainty variables, multiple objectives, one or more. All right. To talk a little bit about these random variable distributions, and then we'll take a break. Okay. So what we just looked at was a case where we use something called the normal random distribution, which means you know an expected mean value, the average value, and some measure of how variable, how wide the variability is, something called standard deviation. So that would look something like this. So the normal distribution, this is a function. The higher the function is, the more likely that value is, okay, on the x-axis. So generally speaking, if your mean or your average was 0, okay, and your standard deviation was 1, okay, the probability graph of values would look like this. Okay, this is the definition of normal randomness, normal random distribution. What the standard deviation means is there's a 68% chance okay, that the value is going to lie one standard deviation under the mean or one standard deviation above the mean. Okay, so I'm going to think back real quick. Our January sales numbers from that example we just did was a mean of 1.8 million, and I think the standard deviation was something like, let's assume 100,000. Okay, what that means is there's a 68% chance that the sales in January will be between 1.7 and 1.9 million. The mean minus a standard deviation, the mean plus a standard deviation. If you go out 2 standard deviations away from the mean, so if you allow it to go up to 2 times the standard deviation below the mean, or 2 standard deviations above the mean, there's a 95% chance the value will lie in that range. Okay? If you go out 3 standard deviations, you're up to 99.7%. If you go to 4, it's like 99.999 something, right? So the normal distribution, you don't have to memorize these numbers, by the way, unless you want to. But the normal distribution just says there's an expected value, and the probability gets smaller and smaller the further away from the average you get, until the probability effectively is 0 if you get out very far at all. So standard deviation is just a way to measure how wide or how far you can get away from the mean before your probability starts just trailing down to 0. And that's what this distribution looks like. There's a whole, you can do a whole mathematical class on why the normal distribution exists and how to derive it and what it means and how somebody came up with it and so forth. But effectively, it is what it is. It's a statistical fact, I guess, that you can define this distribution, and it comes up in a lot of ways in the real world, which is why we use it. But there are other ways you can parameterize uncertainty. There are other kinds of distributions you can use to represent uncertain variables, things that you want to randomly select. Okay? For example, you can have a uniform distribution, which just says there's a minimum, say A, and a maximum B, and the probability of any value in that range is the same as any other value in that range. That is, they're all equally probable. However, there's no probability or a 0% chance you will be under A or over B. That is, you have a cap, minimum and a maximum, that you'll never violate. That the probability is 0 that it's outside that range. But within the range, all values are as likely as any other. That is, you don't have any reason to believe the value is close to A, close to B, close to the middle, or anywhere else in between. Okay? That's just called a uniform distribution because it's uniformly probable throughout that range that each value will occur. Okay? Does that make sense? So that's two random distributions. In Analytics Solver platform in Excel, there's 2 functions that you can use, okay, to tell it this is my random value or my random distribution I want you to pick from. For a normal distribution, you have to specify the mean and the standard deviation. For the uniform distribution, you have to specify the minimum and maximum. Okay, that's enough to specify everything you need to know about the distribution. All right, here's another one. It's called the triangle distribution because it looks like a triangle. And really what a triangle distribution is you still have a minimum A and a maximum B. There's no chance that you'll pick a value less than A or bigger than B. There's the minimum and the maximum, the bound. However, the values in between are not equally likely. In fact, there's one value somewhere in between, not necessarily the middle. Okay? Let's call it C. There's one value that's more probable than any other. And all the other values between A and C or C and B just follow sort of a straight line degradation of probability. That is, the closer you get to A, the less likely that value is going to be selected or chosen. The closer you get to B, the less likely it will be chosen. However, if you go the other way, the closer you get to C, the more likely that value will be chosen. C is the most likely value, A and B are sort of the least likely values that are still possible. Anything less than A is impossible. Anything greater than B is impossible. Okay? And so the probability distribution just looks like a triangle. That is, probability is 0 for anything less than A. As you go from A up to C, the probability gets better and better. That is, the probability of the value, whatever value you want to look at between A and C, is bigger and bigger the closer you get to C. But then once you get to C, that the value becomes less and less likely up till B, at which point it's impossible, or 0% chance beyond B. Okay, so those are 3 distributions: normal, uniform, triangle. The triangle distribution in Excel or anywhere else can be parameterized just by 3 values: A, B, and C. That is the minimum, the maximum, and then the sort of value in between that's the most likely one. Okay, so given those 3 things alone, you define the triangle distribution. Okay, so for whatever values you want to select for A, B, and C.
So is it drawn that way in order to delineate that the likelihood of getting an absolute value in between A and B is lower than getting an absolute value between A and C is lower than between C and B?
Okay, let me repeat your question because I think I understood it, but I'm not 100% sure. You're asking about the way it's drawn, and in this case, C is closer to B.
Right.
Okay, that was somebody picked that. Somebody thought this C here was the most likely value. It's true that the probability of a value between C and B is less than the probability of a value between A and C.
Mm-hmm.
Yeah, because just looking at the size of those individual triangles. That's just the way that distribution is designed to work. I'm not saying it's the only way a distribution could work, because this is just one possible distribution you can use. But yes, that's true in the sense that your selection of C is both the most likely value, but it also sort of dictates how likely the values are less than and bigger than it, by virtue of the fact that the lines will be straight, that the probability graph lines are straight, for simplicity's sake more than anything.
So, like, let's say that if A was 1 and C was 7 and B was 10,
Okay.
then are you saying that we'd be more likely to end up with a value of 6 than we would a value of 8?
Yes. Okay. So, yeah, just to repeat, if A was 1, B was 10, and C was 7, so it's closer to 10 than it is to 1, then it's more likely to get a 6 than an 8. Because if you just look, if we were looking here, so if C is 7 and you went down by 1, the probability of the 6 here is pretty high. If you went down that same amount, so the gap here is the same, then the probability of a value 1 bigger than C is obviously much less. Yeah, so this value is less than this value. Yeah. Yep. Good question. Shows you're trying to understand, and definitely, yeah, that's the right understanding of how that distribution works. So normal, uniform, triangle distributions. I'm going to give you 2 more. Okay. The good news is, I think they're a little easier to understand. Okay. We'll see. One is called the Bernoulli distribution. I should have put the name on here. It's named after a mathematician named Bernoulli. It's really easy. There's only 2 possible values, okay, 0 and 1, or you can substitute any values you really want, but generally speaking, we'll just use 0 and 1. So there's a probability that you'll choose 0. Say that probability is called P. And then there's a probability you'll choose 1, which would be 1 minus P, or 100% minus P. So there's only 2 possible answers, which means knowing the probability of one, and you can infer the probability of the other. Now, it's not necessarily true that 0 is always more probable than 1, right? Depending on your selection of P, this whatever value you want to use for P here, you'll either get a higher probability for 0, lower for 1, or vice versa. But it's a pretty simple distribution because there's only two outcomes, and there's only one parameter, p. Okay, because you'll always have the same two outcomes, 0, 1, and all you need to know is the probability of the 0, which infers or implies what the probability of getting a 1 is. Okay, so that's a Bernoulli distribution. Bernoulli distributions, I'm not even sure I'll give you an assignment to use one, but they're very useful in cases, say, where you want to select randomly either a yes or a no, to do something or not do it. For example, I think in the past anyway, I've given a homework assignment that involved a door-to-door salesman, and part of the uncertainty of being a door-to-door salesman is whether or not you find somebody home when you go and knock on the door. There's only two possible outcomes. Somebody's home or somebody's not home, right? So a Bernoulli distribution is how you could represent that uncertainty, because there's only two possible things could happen. And you just need to know the probability of them, okay? So that's a Bernoulli distribution. This one's going to be a little bit more complicated. It's a little small on the screen. It's called the binomial distribution. And it's not that complicated. Effectively, a binomial distribution is if you had a Bernoulli distribution and you randomly selected from it n times, then what's the cumulative or the sum that you would get? So if I selected from a Bernoulli distribution one time, I'd either get a 0 or a 1. However, if I selected a value from a Bernoulli distribution two times independently, I could get a 0 and a 0, I could get a 0 and a 1, I could get a 1 and a 0, or I could get a 1 and a 1. Okay? So there's three possible outcomes for the sum. I could either get a sum of 0, a sum of 1, or a sum of 2. It's most likely that I'd get a sum of 1 because there's two conditions or two scenarios where the sum would be 1. I could get 0, 1, or I could get 1, 0. There's only one case where I'd get a sum of 0, and only one case in which I'd get a sum of 2. If I had a Bernoulli distribution and I randomly used it to select a value once and then a second time and added them together. Okay? That's a binomial distribution. Where a binomial distribution is parameterized by n, how many times you select from the Bernoulli distribution, and p, which defines the Bernoulli distribution. That is the probability of a 0 each time. Okay? So this graph here represents technically three different binomial distributions. Okay? The blue one, the blue lines are the probability of a binomial distribution if you selected 5 times a value from a Bernoulli distribution, where the Bernoulli distribution was half likely to give you 0, half likely to give you 1. Okay? That means there's a very, very small chance you'd get all zeros. There's a very, very small chance you'd get 5 1s and get a 5. Most likely you'd get a value somewhere between 2 and 3, because you'd get a couple 1s, a couple zeros, or a few zeros and a couple 1s, right? So that's this blue line or blue set of lines is the probability of the binomial distribution selecting 5 times from a Bernoulli, where the Bernoulli is equally likely 0 and 1. The red lines, same thing, except the n, the number of times you select from the Bernoulli, is 20. So now suddenly, it's very hard to see on the screen, but the most likely value of that Bernoulli distribution is 10. Because you'd expect half the time you'd get zeros, half the time you'd get 1s. So over the course of 20 times, you'd get roughly 10 1s. Okay? But you might get as many as 20 1s. You might get as many as 20 zeros. So that binomial distribution is wider. Okay? The range of values it can give you is wider. And as a result, it's a little bit flatter. That is, it's kind of squashed down and stretched out, left to right. The green lines are a binomial distribution with n of 50. So now you've done 50 coin tosses, effectively. Bernoulli distribution, just heads and tails, zeros and 1s. You've done that 50 times. What's the probability, of getting 50 heads? Well, it's very low. more than likely you'd get something like 25 heads, 25 tails. That is 25 zeros, 25 ones. Okay, but you might get as few as 0. You might get as many as 50. Okay, that's a binomial distribution. Okay, so Bernoulli distribution may be the easiest one, although uniform's pretty simple. But Bernoulli distribution is pretty simple. 2 outcomes, 1 parameter. That's all you need to know. Binomial distribution is just an extension of that, where you just repeat the Bernoulli distribution, repeatedly get values from it n times, okay, and see what's the cumulative or the sum of what you got. All right. Now the good news is I'm not going to teach you any more variable distributions, okay? Not that there aren't any, but not any that we'll possibly use, okay? Okay, so that takes care of understanding how we might represent or parameterize the uncertainty we have when we're doing a simulation problem, okay? We have these effectively 5 distributions, plus many more if you want to learn about them, but these 5 at least that we could use to help us parameterize or determine how uncertain we are about various things in our model, okay? More likely than not, we'll focus on normal distributions, uniform, maybe some triangle distributions, okay? I definitely want you to be aware of Bernoulli and binomial distributions. They're mathematically not hard to understand. They do come up, for example, when you have 2 outcomes, it's nice to you have a distribution to represent that. And then if you have to repeat that over and over, that is, your door-to-door salesman goes to 10 houses, well, there's a chance that somebody will be home or just not be home each time. So that's a binomial distribution that would tell you how many houses had somebody home. Okay, so that comes up relatively often as well. So that takes care of random variable distributions. Let's take another break for the night, and then we'll come back and do a final example with simulation. We'll do it from scratch. So you'll watch me build the Excel spreadsheet, use the variable distributions, use a couple of them anyway, how you set those up, determine those, parameterize them, and then run the simulation and look at the output or the objective. Okay. All right, so we'll take a 10-minute break. Okay.